Hello, my name is Muthu, and I'm currently the electronics team lead for the Duke Robotics Club. And in this presentation, I'll be discussing the technical details of the electronics stack. All right, so in the electronics stack, we have four main subsystems. Namely, we have one subsystem dedicated towards power conversion and distribution, one dedicated towards sensing, as well as our embedded systems and embedded controls, one subsystem that deals with our computer and network and that stuff, and then one system that deals with acoustics and acoustics processing, acoustics filtering, and that type of thing. All right, so let's first start off with power conversion and distribution. I'll be jumping from this to sort of a system guide, system document that describes the interconnections between various components in our system. So you'll see more graphics and all that. So, okay, anyways, first of all, power conversion and distribution. So this system is responsible for basically taking power from the battery, making sure that it's safe and all, making sure that we're able to switch the battery off, switch it on and all that, and then converting the voltage from the battery, which currently we use a lithium polymer battery, converting that voltage to the appropriate voltages required by the various electrical components in the stack. So currently our battery sits at somewhere between 14 to 20 volts during the run. Due to the LiPo batteries, they can be any voltage in between, but our various components use different voltages, and so we require power converters to convert the voltage to those. The power conversion distribution system also has fuses for safety, making sure that in the case of a short or anything, the stack doesn't catch on fire or anything. The fuse will blow before that, allowing us to be sure that everything's safe. And then we also use relays as switches. And at least right now, currently we use off-the-shelf voltage converters. So let's discuss the actual details. So located here, you can see that we have a system diagram of our electronic stack. This is the entire system. So right now, I'll be going through it piece by piece. So first off, let's start with the electronics. Let's start off with the power conversion and power distribution. And I should also note this diagram represents what we believe to be next year's robot. A lot of this stuff is similar to the previous year's robot, namely Cthulu 2.0, but there are some differences that I'll go over. All right, so first off, in our new system, we're going to have two battery capsules. The batteries will be located outside of the robot, and so they will connect. So they will connect to the inside of the robot, the main capsule, via underwater connectors. And so when they connect to the inside, they'll first connect to a PCB that determines which battery to use. Namely, this allows us to use a hot swappable system where we can plug both batteries in and then remove one, making sure that the current doesn't fluctuate or the voltage doesn't fluctuate randomly. This way, we can keep all our components on when we want to replace the battery. After this PCB, after this custom PCB, the single power signal that comes out, since we're choosing from one of the two batteries, it goes to the relays. And so we have two relays. The relays are basically electrical switches. Whenever you turn it on, you allow the current / voltage to pass through. When it's off, nothing passes through. It's basically an electrical switch, but if you've heard of a transistor, it has the same sort of function, except this is much more stronger. This is much more, there's no leakage current or anything like that. And so to actually activate the relay, we have physical switches. And so whenever they're powered on, i.e. there's a connection from positive to negative, whenever we turn them on, it allows the voltage from the battery to continue to go through into our main system. When it's off, nothing happens. So the reason we have two relays is that one of our relays is for the delicate components in our system, like the computer, the switch, the DVL, which I'll get into later. But basically, these are the low current, low power components, whereas the other relays for the more high current, high power, like thrusters and servos. The reason we separate this out is mainly because we don't want any like back current or back voltage to affect the other parts of the system. Like if there's some fluctuations in the thruster voltage or the thruster draw, we don't want that to accidentally fry the computer or something. So this effectively isolates the two parts of our system with respect to each other. Okay, so that's the relays. And so once assuming that the switches are on, power is being applied, the robot's on. That means the robot's on. We now go into the actual power converters themselves. And so currently we're using off-the-shelf converters. We plan on trying to convert these to PCBs in the future, but as of now, everything's just off the shelf. And so each of these, they basically convert the voltage from one value to a different value. And so we currently, we have a power, so the thrusters, they use straight battery power, whatever voltage the battery's at, that's what the thruster's at. For servos, we convert it to 7 volts. Required by our servers. The Jetson goes to 12 volts. The switch goes to 48 volts. The DVL will need to go to 24 volts. And then ignore the FPGA, but we'll have a second computer that will also require another power converter. So all of these allow, they provide the power for the other components in our system so that they can function and do what they need to. And so that is basically, that's the fundamentals of the power distribution and conversion subsystem. All right. Next, we have sensing and embedded controls. And so this system is involved in, I guess, 2 main things. We can probably even split it between sensing and embedded. But sensing deals with trying to get data about the outside world into the computer so that the CS team can then take this data and then process it and do whatever they want with it. And so we have a bunch of sensors on board, including an IMU, DVL, cameras, pressure sensor, and then hydrophones. And we also have a joystick that we can attach when we are tethered to our local computers. I'll go over a brief overview of each sensor. So the IMU stands for the inertial measurement unit. It provides the orientation of the robot, like specifically the rotation of the robot, roll, pitch, yaw axes, so on. Of the robot, so that helps with state estimation with CS. The DVL provides absolute velocities for the robot, so like how fast the robot is moving in each of the directions X, Y, Z, also used in our state estimation program. The cameras obviously are cameras that provide images used by computer vision and all that. The pressure sensor, we're still currently integrating this, but the pressure sensor, it provides the pressure value, which we can convert using the standard physics formula. We can convert that to depth, which is Z value. And then the hydrophones, they basically collect acoustic data for the our acoustic algorithms, which I'll be going into further detail later. The joystick is standard joystick that we connect. I believe it's an Xbox joystick. Yeah. Then in terms of embedded controls, our embedded system, our main embedded system is an Arduino. We use an Arduino Nano. This Nano, in terms of the actual controls, it connects to a multiplexer. This multiplexer basically gives it, it makes it act like it has more pins than normal. The Arduino by itself, I think it only has 2 or 3 pins that we can use for PWM. Attaching it to the multiplexer, we're able to get 16 PWM-able pins using this specific multiplexer with a simple-to-use API that we can call in our code. And this multiplexer, we're able to control it that sends PWM signals, specifically like how low or how high this to the ESCs. The ESCs are the things that control the thrusters. So, we can, using this, we can set the speeds to the thrusters. Namely, the PWM sets the speed. The ESC does the low-level stuff of converting the actual PWM signal into a 3-phase AC value that the thruster can, that's what the thruster uses in terms of power. And I should also probably mention ESC, I believe it stands for electronic speed controller. This is just a standard thing that does the very, very lowest level of controls over devices such as thrusters and motors and stuff like that. But that is our embedded controls. For the pressure sensor, our pressure sensor, we can't directly connect it to the computer or anything. It first requires, so the Arduino connects to a level shifter, which then connects to the pressure sensor. So the level shifter is, namely, it allows the pressure sensor, which is at 3.3 volts, to be converted to a 5-volt signal that the Arduino can read. In addition to this, all of our code, we maintain the ROS packages, datapub, offboard comms, AVT, camera, and joystick in our GitHub code base, which I will be discussing later. All right, so I just want to go over, again, like the basic fundamentals of everything in the sensing, more in terms of the diagram here. All right, so let's start with sensing. So IMU, it's directly connected to our computer via USB. Very simple to do. Our DVL, so our DVL is a bit special. So our DVL sits outside of the robot. I should mention the IMU is inside the robot. Anything here is outside the robot on this left-hand sort of line. So the DVL is sits outside the robot, and then it's connected to this thing called the RS-232 converter. So the DVL provides an RS-232 signal. That's a specific type of serial signal. And then we have a converter that converts that to USB, which then we connect to the computer. Pretty simple. The cameras are Ethernet cameras. The cameras sit here. There's just one here, but this is just generalized. We currently have 3 cameras on our robot. The cameras go and are connected to the Ethernet switch, which I'll get into later, but they are simply networked cameras based on Ethernet and that sort of signal. All right, and okay, and so in terms of our embedded systems, so the Arduino is connected to our computer via USB. That's this location here. Beyond this, beyond this, so the Arduino, as you can see, is connected to 2 things: the multiplexer and the level shifter. So I'll go over the level shifter first because it's pretty simple. So we connect one of the ports, one of the I2C ports, to the level shifter, and then the level shifter to the pressure sensor out here, which is outside the robot, measuring the pressure. And I should note that both of these use I2C as their communications protocols, so we just connect them together. It's not represented as such here. But you would just connect them and split it out between the 2. The multiplexer also uses I2C, so we connect it to the Arduino as well. And so the Arduino, it requires there are 4 signal wires that go into it, but it gets generalized to 8. And so this multiplexer then connects to 8 different ESCs. And so these ESCs are then connected to various thrusters on the outside, located here. And the ESCs, of course, they also take power from the battery just so that they can power the thrusters. Similarly, the multiplexer also collects data for the servos. So it will be connected directly to the servos on the outside. Servos are located here with power from the servo PCB going into the multiplexer and passing through the multiplexer into the servos. So the battery goes, so I just want to make this clear, servo power, it goes to the multiplexer, and then multiplexer provides servo power, basically just passing it through its rails. Whereas for the thrusters, the batteries connect directly to the ESCs, which then provide the power for the thrusters. Only the signal wire from the multiplexer is connected to the ESC, providing that value. And I believe that is, yes, I believe that's it for the embedded systems of our overall electrical system. All right, so next, our computer network. So this is pretty simple, in my opinion. It's basically just the computers we use, as well as the Ethernet switch that we use to distribute the network to various devices. And so we currently only have 1 computer on board, but we will be using 2 computers, mainly due to some compatibility issues dealing with the Cellier, which requires x86, while we need ARM for the GPU. There's some just difficult components there. And also I should mention that whenever we do tethered runs where we communicate with our laptops, our personal laptops, with the onboard computer, we have a router on the outside that distributes the network to all of us. And the router is connected to the switch on the inside of the robot via an Ethernet cable, namely the tether. And so let me just go over this pretty quickly. So I already sort of showed you the basic principles of where stuff is connected. So as I'm sure you sort of guessed, this is the Jetson, also known as our computer that we're planning on using. And so it's the computer connects to all the devices mostly through USB, and then connects to the Ethernet switch via Ethernet. So that provides the network. And the Jetson is the DHCP server that assigns all the IP addresses. I have another presentation that describes that, so I recommend viewing that, namely the systems engineering presentation. The Ethernet switch, again, it basically, like I mentioned, connects to the cameras, connects to the tether to the outside world, which is what we connect to the router, and then connects to the computer. And I should probably also mention Jetson and Ethernet. They have their own power converters that I mentioned before. And so that is our computer and networking system. All right, and then finally we have acoustics. And so the acoustic subsystem, so this is targeting a single task with regards to acoustics, namely the acoustics task, which the overall task is literally we need to identify the location of an underwater acoustics pinger. And it is much more difficult than it sounds. It's really difficult. There's a lot of math and signal processing that's involved there. But the thing is, it is worth the most points out of all the tasks in the competition. Just so that I think that itself shows how difficult it is. So it's definitely very difficult, and we've dedicated like the last 4 years. We've had a team trying to get a good algorithm working, and we think we're nearly there to getting at least a decent trial which works for at least some amount of the time. So in terms of the hardware for acoustics, we collect data using some hydrophones. I believe in the future we will have 2 separate sets of hydrophones. Currently we only have 1 set, but and we'll connect these to a device called the Salier. And this Salier, it basically performs simultaneous analog sampling of the hydrophones, allowing us to actually collect the data in a digital form that we can then transfer to our computer with USB and process and analyze that. In terms of software, we have the acoustics package that where it's not yet in master, but we're nearly done with it. It samples the data, finds the it makes a guess for where the pinger is by finding the quadrant of the pinger, and then uses a more sophisticated technique to get the actual horizontal angle to the pinger, or at least what we believe to be the correct horizontal angle. And so let me just show you the last parts of this. So basically here we have 2 sets of hydrophones located on the outside of the robot, and so they will be going into an acoustic PCB that does some basic signal processing like anti-aliasing and just signal filtering. These will then connect to the Salier. It's not pictured here, you can ignore this, but these connect to the Salier, and then the Salier will connect to the RockPi, which is our second computer that is x86, and then RockPi will connect to the Ethernet, providing it with access to the other computer and just access to the system in general. And so this is, I believe, this is our overall system. I'm going to take a few minutes just to describe our code base, namely the packages we maintain. I just want to point them out and just detail what they do. So the packages we maintain in onboard in the electronics team. So we maintain AVT camera. So this is basically the package that interfaces with the cameras and publishes the image data so that other packages like CV can use this image data. This basically is the camera driver package. We also maintain data pub. So this has a couple of scripts that does publishes the data from various sensors. So it publishes data from the DVL, converts that to an odometry message that the other system, the sensor fusion packets can use. It also publishes data from the IMU, and then it converts data that is the pressure coming from the pressure sensor, converts that to depth using the standard physics formula. Another package we maintain is offboard comms. And so offboard comms, this is how this is where our Arduino code lives. So our Arduino code located here contains the basic Arduino code that we upload to the Arduino, and it's basically a standard ROS node on the Arduino that executes, and it's able to subscribe and publish to topics. And it subscribes to like things like the thruster values that's being provided by controls, and it then gives the signals to the multiplexer and by extension to the ESCs about how fast to go on all of that stuff. But this is where our Arduino code lives. And then I'd just like to mention the sensor fusion package. this is basically just a package that's very important to us, because beyond this is everything CS has to do, but sensor fusion, it basically just combines all the sensor data into a single state estimation. In terms of the land side workspace, we maintain both camera view and joystick. Camera view is a very basic package that it allows users to view, save, and load video streams and files. Basically, it allows for mocking the camera when we don't have access to the physical camera. And we maintain the joystick package, which joystick is, it just allows us to use a joystick with the robot and controlling the robot with the joystick. And so, yes, that is all for the electronics stack. Yeah, this is basically a general overview, and well, I hope you got a basic understanding of how the electronic stack works. Thank you for watching.